Okay, section 8.2, trig proofs. Yay! Okay. Yesterday we learned our 8 identities. So if you do not have your space notes, you may want to get those. But if you do have them, take them out because you're going to need to reference back to them. So you're going to need your 8.1 out. So what's the difference? Proofs. I'm telling you that this is what it equals, and your job is to prove it. Make it show me and tell me why. As you're going through proofs, you want to choose the side that is the least complex as the solution side. Typically, it's going to be the right-hand side, but sometimes it is switched. But typically, it's going to be the right-hand side, but you're looking for the least complex side, and that's your goal, okay? You want to look for any algebraic manipulations. If you need to add fractions using to get a common denominator or something. Remember, also, you can remember chopsticks in a bowl. That's the site you're going to work from. So the least complex is your solution. Oh, yeah. Chopsticks in a bowl. Okay, in case you don't remember chopsticks in a bowl, that's when we have two fractions with different denominators. We can cross multiply. 1 times 3 gives us 3. Then we add, cross multiply. 2 times 1 gives us 2. And then we multiply the denominators. Chopsticks in a bowl gives us 6. And we end up with 5/6, right? So when you're adding fractions or subtracting fractions, keep that in mind. We can factor, we can multiply out. After you check for those things, you want to look for trig substitutions. So thinking of your basic 8 identities, change everything. So using your ratio, your reciprocal rules, Pythagoreans, and then change everything to sine and cosine, and or cosine if possible, or if necessary. Okay, you want to replace your squared expressions with Pythagorean identities. So if you see if it's cosine and cosine squared and sine squared, see if it's going to satisfy the Pythagorean identity. If you see tangent and secant, see if it satisfies the Pythagorean identity. And if you see cosecant with cotangent, see if it satisfies. Okay. Keep looking at the answer. So keep looking at your goal and see, okay, am I there? Am I there? All right. Now, before we dive into solving proofs, we're going to talk about ways and algebra tools that you should use. So here we have tan theta plus 1 squared. Before we look at it as a trig, we're going to look at it as a traditional algebra problem. If you had x plus 1 squared, what would you tell me to do to expand this? I would multiply x plus 1 times x plus 1, right? And then we would apply good old FOIL, right? And we would go through the whole process, get FOIL, x squared plus 2x plus 1, right? Guess what? Same thing applies when there's a trig in play. So if I have tan theta plus 1 squared, what that means is that I have tan theta plus 1 times tan theta plus 1. And I would go through FOIL. So I would go through FOIL. After I go through FOIL, I end up with tan squared theta plus 2 tan theta plus 1. Okay, so that's how I would expand and multiply. Is it that much different than algebra? No. Glad you see that. Okay, here. What if I wanted to condense? So I want to multiply to condense. Here I have secant theta plus tan theta times secant theta minus tan theta. So in terms of algebra, if I had x plus y times x minus y, what would you tell me to do? There we go. This is a 2 binomials that have the same addendums but opposite signs, right? So that it condenses down to being x squared minus y squared. So what do you think is going to happen with the trig? I have the addends are the same, but plus and minus. So what does this condense down to? So it comes secant squared theta minus tan squared theta. Yes. All right. On to the next. All right. So back. So we also learned if I had x squared minus y squared, what does that factor out to become? So it becomes x plus y and x minus y. Okay, remember this is called difference of two squares. Two squares. So anytime I'm subtracting two perfect squares, they factor out to be this pair of binomials. So in this case, am I subtracting two perfect squares? Yeah, so it's going to factor out to be sine theta plus cosine theta times sine theta minus cosine theta. I meant to change colors and pens, but I didn't, sorry. Okay, and that's following our factoring rules, difference of two squares. Okay, next factoring rule that we went over in real life was simple trinomial factoring. Okay, so if we had x squared, yeah, I'll finish, x squared plus 2x plus 1, how would we factor that? Yeah, because we're asking ourselves what multiplies to give us 1, but adds to give us 2, right? And that would be x plus 1 times x plus 1, which equals x plus 1 squared, right? So in this case, we have cosine squared theta minus 2 cosine theta plus 1. We're still asking ourselves what multiplies to give us 1, but adds to give us -2. The only difference is instead of our x's, we have cosine. So it would be cosine theta minus 1 times cosine theta minus 1, which condenses to cosine theta minus 1 squared. So again, the algebra skills that we already have are still going to be applied here. The next algebra skill we talked about was greatest common factor. If I had 2 plus 2x, what would you tell me to do? I can factor out 2 from each term, right? And I'll be left with 1 plus x. Correct? Okay, same skill can be applied with trig. So now I'm asking myself, what is the GCF here? What is the GCF between these two terms? Tan. So instead of 2, we have tan theta. We're going to factor out tan theta. And we're left with 10 divided by tan is 1. And then we're just left with sine. Okay, so GCF can still be applied if necessary. Okay, and then our last tool here, if I had 1 minus x to the 4th, this is still difference of two squares, right? To find the difference of the two squares, you're taking the square root of each term. So the square root of 1 is 1. Square root of x to the 4th is x squared, right? And I'm left with 1 minus x squared and 1 plus x squared. However, this is another difference of two squares. 1 minus x squared is still two perfect squares being subtracted, right? So that can factor even more, and it factors to 1 minus x times 1 plus x. This is not difference of two squares. It's the sum of two squares. So can I do anything to it? No, it's actually a imaginary, well, complex number situation over there. So this would be that fully factored. The only difference here, instead of x, we have what? Sine. So x equals sine theta. So in the end, all said and done, this is going to come down to being what? There we go. So the purpose of 1 through 6 is to show you that your trig expressions are still unknown variables, which means that the things we can do with x, we can do with them. Does that make sense? All right. So that's the foundation there. Let's dive in. So now for trig proofs. What makes a trig a proof is that you're given the answer. And your job is to prove it. While you're proving it, a proof means you told me why you did something, okay? So when it says you're working the most complex side, this side is what we're working. This side is our least complex, so this is our goal. This is our solution. Our goal is to get this into that. Okay? So going through your checklist, you ask, is there anything I need to multiply, combine, reduce? And you're like, no, 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 no. So then you're at the point, all right, there's nothing, there's no squares, there's nothing. Can I turn everything into the terms of sine and cosine? Pause the show. Come on, just full attention. It'll still be there. Okay, can I turn it into everything to sine and cosine? The answer is yes. I can take tan by using the ratio rule, and it's going to become sine over cosine divided by the sine x. So that's the first thing I did. So first I use ratio to turn it to sine over cosine. Next, what am I going to do? I'm going to keep, change, flip. So second, I'm going to divide. So keep, change, and flip equals sine over cosine times 1 over sine. That's going to cause my sine to eliminate. And I'm left with 1 over cosine. And what happens here? That equals. So third, I can use the reciprocal and get that equals cosecant. I wrote things all weird. Secant x. And that is my proof. X is the same thing as theta.
Why is the sine of the cosine not have that?
Because I forgot to write it. A lot of times when I'm showing my work, I fail at writing the extra variable in.
Okay, so
Wait. Why are you multiplying by 1 over sine? But wouldn't it flip to be sine over 1?
It's already sine over 1. In the denominator,
Oh.
it's already sine over 1.
Yeah, so wouldn't it flip to be?
Become 1 over sine. This is already sine over 1. So we keep, change, and we flip, and that's why it became 1 over sine. If it's a whole number in the denominator, it's still going to be a whole number. Its reciprocal is fraction. Okay. All right, so this is considered level 0. How do we feel about level 0? Good? Not good? All right, we're going to move up a level. All right, now we're at tan x plus cotangent x equals cosecant times secant x. This is our goal. Our goal is to go from tan x plus cotangent x to secant x times cosecant x times secant x. So we go through our checklist that we have written down. We're like, okay, is there anything I can add? No. Can I subtract? No. Is there any common denominator I need to create? No. Is there anything I need to multiply? No. All right, now we're at the thing. Can I turn everything into terms of sine and cosine? Yes, I can. So step one, I'm going to use the ratio to turn everything into sine and cosine. So tan becomes sine x over cosine x. Cotangent is going to become cosine x over sine x. So I use the ratio. Okay. So the second thing here is I need to get a common denominator. So the second thing I'm going to do is get a common denominator. How you get a common denominator is up to you, but I'm just going to use chopsticks. Sine times sine is sine squared x plus cosine times cosine is cosine squared x all over my bowl. Cosine times sine is cosine x times sine x. Okay. What's going to be my third move?
Sine squared plus cosine squared equals 1.
This equals 1. Next step is to use the Pythagorean. Sine squared x plus cosine squared x equals 1. So I have 1 over cosine x times sine x. What's going to be my fourth move? Fourth, I can separate these. So it becomes 1 over cosine times 1 over sine. And by ratio, what do they equal? Reciprocal. What is 1 over cosine? Secant. What is 1 over sine? Cosecant. And is that what our goal was? Yes, it was. Okay, you only can separate a denominator and or a numerator when there's no more addition and subtraction. Okay. So notice how in my denominator, am I adding anything? Nope. Am I adding anything in my numerator? No. So they can be separated into two separate fractions. All right. Next level, how do we feel? It's a little different. It's a big giant puzzle. And you have to figure out the pieces. Okay. So again, you're going through that thought process. I tried to list out as many things as you should be thinking and analyzing. But yeah. Okay, we're gonna move it up a notch. This is our goal. So our goal is to turn this, because this is our most complex, into that. Okay. Any suggestions on where to start?
Expand.
We're going to expand. So we have 1 plus tan x times 1 plus tan x. And don't forget your cosine squared x. So expand it. Step 2, we're going to FOIL, right? And we get 1 plus 2 tan x plus tan squared x. And that leaves us with cosine squared x. My nose itches. Okay. What do you want to do now? The parentheses matter still.
Distribute the cosine.
We could distribute the cosine squared. Want to do that route?
return the tan squared plus one, the
So what?
set. No,
What is tan squared plus one? It's secant squared minus tan squared equals one.
so it would be. It'd be.
So if you have secant squared minus tan x, I just want to make sure everyone understands what Sam is asking. That equals one, right? So if I wanted to have one plus tan squared x, I would add tan to this side, and what's left over there? Secant squared. So step 3, we're going to use Pythagorean and condense this. I knew that. Daniel, what are you talking about? All right, so we're combining 1 and tan squared x. That's going to give us 2 tan x plus secant squared x. And now we're down to one less term. Now I think our only option, like Daniel said, is to distribute. I thought you said distribute at first, like right here. Huh? Oh, my bad. Sorry for giving you that credit. So we're going to distribute. So end up with 2 tan x times cosine squared x plus secant squared x times cosine squared x. Do you guys remember from yesterday what happens when you multiply a reciprocal times its reciprocal? It's not, it doesn't cancel out, it equals what? 1. So secant times cosine is 1. Sine times cosecant is 1. Tan times cotangent is 1. So this is going to equal what? 1. And this is because of reciprocals. Okay, so we're left with 2 tan x times cosine squared x plus 1. Getting closer. Huh? I am. No, it's just a message. Oh, okay. I'll look at it a second. Not on my watch. No, now I got a missed call. All right, anyways. That's weird. Figure that out. All right, so what happens here is that we can use the ratio rule to get everything in terms of sine and cosine, and we're left with 2 sine over cosine times cosine squared plus 1. And what happens to the cosine in the denominator? It takes out one of the cosines. Let me pause. Okay, so the cosines cancel out, and lo and behold, final thing, what are we left with? We're left with it. 2 sine cosine plus 1. I forgot my little x's in there. Let me squeeze them in there. Are those basically the same thing? Yes. Because like multiplication, order of addition, doesn't it matter? No. All right. Talk to me. I didn't say it was a little.
Yeah, nothing, right?
I'm being nice. Also, I won't be here, so I didn't trust y'all not to use them. So I just admitted to myself that you probably use your notes. Therefore, I'm not lying to myself. Okay. All right. Challenge. You're going to do this one. This is your goal. And your hint is to start with chopsticks in a bowl. Go. So your hint was to do chopsticks in a bowl. So I'm going to chopstick it out. That's going to give me 1 plus secant x plus, chopstick it out, 1 minus secant x, and then my bowl. That gives me 1 minus secant x times 1 plus secant x.
Wouldn't there be like minus in X on the top? Oh,
It is. So that's step 1. Now I'm going to simplify and reduce. So when I do that, the secants cancel out. 1 plus 1 is 2. This is difference of 2 squares. So it becomes 1 minus secant squared x. All right. So there's nothing left for me to do. However, in 3, I'm going to use the Pythagorean. And the Pythagorean that I'm using is secant squared theta minus tan squared theta equals 1. So if I want to have 1 minus secant squared, I would have to subtract. And if I subtracted that, what is left by itself? Oh, good old negative tan. So by Pythagorean theorem, I'm left with 2 over negative tan squared x. And then step 4, I'm going to use the ratio because 1 over tan is what? Cotangent x. And that is how I go from there to there. So I combine the 2 fractions. Then I use difference of 2 squares to condense the denominator. Then I use Pythagorean theorem identity with secant and tan to substitute in for the denominator. And then I use the ratio to go from being tangent squared to 1 over tangent squared to being cotangent squared. Questions? See where you went wrong. Okay. All right. The problem here is that when you're doing these, there's going to be so many like different little things that can go wrong. Okay. That's why I said keep looking at the answer. This is my goal. This is my goal. Okay. Our goal here is to become cotangent x minus cosecant x. That's our goal. Currently, we are cosine x minus 1 over sine x. Okay. What I want to show you here is notice how in your denominator, you are not adding or subtracting anything, right? What that allows for you to do is to separate. So this allows for you to go to separate into 2 separate fractions. So you can split. That's because in my denominator, am I adding or subtracting anything? Answer is in the denominator, no, I'm not. As long as I'm not adding or subtracting my denominator, that allows me to split my numerator. Exactly. Just by doing that. And then I can use ratio and reciprocal. Ratio tells me that cosine over sine is cotangent, and the reciprocal of 1 over sine is cosecant. Okay, so knowing that little bit of rule that I can separate makes it way more easier to comprehend what to do. Yes. Okay. Our last one. This is our goal. Right now we have 1 plus sine x over 1 minus sine x. All right, so looking at this one, can I separate? No. Why can I not separate? There's subtraction in the denominator, so I cannot separate. 1 plus sine x over 1 minus sine x. The strategy we have to use here is called a conjugate. Okay? Conjugate is just a fancy way of saying you're multiplying by a fancy one. So we're going to use what's called a conjugate. And I think I spelled that right. Your conjugate is the opposite operation. Is that right? It's the opposite operation of your denominator. So in my denominator, I'm currently doing what? Subtracting. So the opposite of that's going to be adding. And if I do it to the denominator, I also have to do it to the numerator. Okay, that's why it's called a fancy one. Because anything divided by itself is 1. So I'm really not changing the value of the original expression. I'm just changing how it looks. Okay, I had a teacher who called it the conjugate costume. Okay, I'm putting on a costume, but underneath it's still the same. Okay. So this is going to give me 1 plus sine times 1 plus sine all over 1 minus sine x times 1 plus sine x. Which equals, so I'm going to FOIL, and I'm going to use difference of 2 squares. So foiling and using difference of 2 squares, I'm left with 1 plus 2 sine x plus sine squared x all over 1 minus sine squared x. Okay. Nope. You can't cancel anything out when there's that addition and subtraction. Okay, what is 1 minus sine squared x?
Oh.
So with Pythagorean, good old Pythagorean, no. This is all over cosine squared x. And I guess we'll pick up here, or if you feel challenged, you can finish it.